All right, everyone, welcome to another episode of Robo Papers. Today, we are super glad to have Ilia Larchenko with us today. What led to this is I've been following actually Ilia on Twitter for quite some time, and I thought that he just have the coolest demos that he's been doing, especially on the robot ecosystem. So yeah, super glad to have you, Ilia. Maybe as a start, if you can share a little bit about yourself, how do you get into robotics and all that? Yep.
Yeah, sure. Thank you for inviting me. Really glad to be here. Yes, I think as you mentioned, maybe I have a bit unusual profile for the guests of this podcast. So in my career for the last, let's say, 13 or 14 years, I was mostly working in data analytics, later data science and machine learning, but mostly not in research, but I worked on applied business problems that are solvable by machine learning. And also a few years ago, I was very active in machine learning competitions and used to be top 20 on Kaggle and so on. So I have broad experience in machine learning, but none of it experience was actually professionally related to robotics. So I've never worked professionally or did professional research in the robotics area. But yeah, you may ask what I'm doing here. And here because I'm doing robotics as a hobby, and I think I started around 9 years ago or so from some simple robotics experiments, and then it's evolved over time. I had some ups and downs, some breaks in this 9-year journey. And currently, maybe last year or so, I started to experiment mostly using the robot library with some things on the intersection between machine learning, AI, and robotics. And yeah, this robot ecosystem actually allowed me to do all these things. So this is why maybe today I will have some focus on the projects on the library and robots. But yeah, if you want to overall describe what we're going to discuss today is how to run some affordable robotics experiments at home if you don't have thousands or 10,000s or even $100,000 for your own robotics library and don't have or laboratory and don't have access to it, but you still wanna run some experiments. So I will share my experience. I will show some of the things that I'm doing in this area, and yeah, and we'll have some demo of what I've been working on recently. I will have 3 main blocks in my presentation today. So the first one, I just want to give you some intro into running robotics experiment at home, and it will mostly be about the robot ecosystem. Just want to give intro for people who don't know about it yet. And then we'll talk about my latest maybe experiment where I led different frontier LLMs to control my robot, completely zero shot. And then finally, I want to talk about some topic that is on the kind of other side of the spectrum of different policies. It's a very simple decoder-only transformer policy that I developed for behavioral cloning half a year ago or so. So let's probably begin. And yeah, first of all, just want to introduce this robot library. So this is the library and initiative developed by HuggingFace. It's a very well-known company in the area of open source machine learning and AI. And around a couple years ago, they started to work in the robotics area too. And they developed this library that allows you to run the whole process of AI-driven robotics experiment, starting from controlling different robots, collecting data using teleoperation, then training some policies and running these policies on the real robot. It also supports a few simulated environments, and it's constantly developing. Recently, there were added support of different VLM models, then there was support of some reinforcement learning models and so on and so forth. So literally, I would say almost every month they have some release that actually push boundaries of this library a little bit, and it's very cool. It actually allows you to start from zero to some really trained policies and your robot doing the actual stuff in real life, maybe some simple things in maybe 1 weekend. So it's very, very easy to start, and then it allows you to iterate and go even deeper. And then, so yeah, sure.
Yeah, I was just gonna say, just to chime in, I think the robot is a huge unlock. It just makes robotics a lot more accessible. So I actually also help to co-organize. Recently they have this worldwide hackathon. So yeah. Chris also helped out as a judge, but I also actually put up the Bay Area version. So we printed a bunch of the Kiwi and SO100 arms. It was super cool, and the fact that it's so accessible that we can even have dozens of bots, like without breaking the bank. It's really like I think really make it a lot more accessible. So again, a big shout out to the folks from Hugging Face for doing this.
Yeah, I think it's very cool, and yeah, it's the main points that makes it accessible. And yeah, I also want to talk about the robots themselves. So I think the main, let's say, robot that natively supported by this library is like this standard OpenARM 100, and also now have the version 101 that is slightly different, but like 99% is still the same robot. And yeah, it's like a simple robotic manipulator, has 5 degrees of freedom plus gripper. And the main advantage of this robot is that it's cheap. So it costs around $130, can be like a little bit more or less depending on where you live. But the main idea is that it's like at least one order cheaper than let's say more professional robots. Again, if you don't have like $1,000 to spend for simple experiments, you can easily afford it and run experiments with this robot at home. Again, of course, it's not as precise as some other robots, so you cannot probably like thread a needle at least yet with this robot. But if you want to run some like simple experiments, it's good enough. And again, it's natively supported by the robot, and you can run all the models on this robot too. And yeah, just an example how it works in real life. Here I'm just showing how you teleoperate this robot. So you usually need 2 arms. So I have like 2 arms. One is a follower, another one is leader. And it's like standard teleoperation setup. When you move the leader, and follower just makes the same movement. This is how you usually collect data set with this arm. It's pretty easy and intuitive. And then if you want to upgrade this robot and actually go with some mobile robot, you want it to like move around your house and so on, you can also use this Lokivi. That it's technically just mobile version of the same robot. It's kind of the same arm on top plus extra mobile base with 3 omni wheels that allows it to move in any direction. And this robot can be both like wired or can be controlled remotely using like Raspberry, NVIDIA, or anything else you manage to connect to it. And again, another nice thing about both of these robots is that they're open source. They like share all the parts that you can like print. They share all the code, and you can adjust it as you like. So I can briefly show you how my current version of the robot of this Lokivi looks like. I hope you can see it on the screen. I will show it later again, but I added a lot of stuff. I have like different cameras, different camera mounts. I have another level on top. I have like another top view camera. So like I added a lot of things to it, and it's kind of keep changing. So I think maybe if I show you this robot 1 week from now, it probably will have new parts and so on. So it's very easy to adjust. It's very easy to iterate. Yeah, so you can also see how it looks in real life. So here I control my robot in like my house. I actually control it using this teleop Android application that I developed during this hackathon that you mentioned a few weeks ago. And so yeah, there are a lot of ways how you control it. So yeah, currently I'm using this application for this purpose. And overall, also related to this hackathon, another nice thing about this library and these robots is that they already have very big community. There are already thousands of people in Discord, and a lot of people experimenting, a lot of people developing some new things, either like in algorithms or hardware or so. So you can find, I don't know, different grippers, different ideas, different libraries that allow to integrate with other things. You can just see and get inspired by experiments that other people running. So all of these are very, very cool. And finally, let me just briefly show you. Yeah. And this is how it looks literally at my home. So this is my laboratory for robotics experiments. So it's happening just on my dining table. I have like a couple of these arms, have like extra top view camera, and just laptop that connects all of these things.
So MacBook's got enough compute for you? Sorry.
Yeah. It's a good question. So for training the actual models, I usually use some cloud GPUs, but you can run some simple models on your laptop too. So in the very end of presentation, I will show you. So this dot policy that I want to talk about, it was able to run on my laptop with like 25 predictions per second. With processing like 3 camera inputs and so on in real time. So it was kind of pretty fast.
Nice. Okay.
But for training, of course, if you want to train some big VLA, laptop is not enough. But for collecting data, running simple policies, it's still okay.
Yeah, is this your permanent setup? Your dining table, like, are you using the leader arm to feed yourself, like, at the dining table?
Yeah, actually, more or less, yeah. So it's been like this for a while. So like this robots occupied like 80% of my dining table. I was actually eating on the like small corner there.
So it's not really a dining table. It's more like a robotic experiment there. Well, it's awesome. Yeah, it's cool.
Yes. Okay, so I think this is it like just about intro. So I wanted to introduce this like library, these robots. And let's move to some of the actual experiments that I've been doing. And so the first thing I want to talk about is this. So I wanted to try to control this robot, not with some trained policy, but with one of the like frontier LLM with completely like zero shot training. So without any training, without dataset collection, just wanted to test how does this biggest LLM can control a robot directly. And in this short video, I just tell my robot that I'm thirsty and that's it. And it's completely zero shot controlled by Claude 3.7 by like sending some commands to robot and processing data from cameras. And you can see that it can kind of complete this simple tasks. Again, no training, no fine tuning, nothing at all, just pure LLMs.
So can I ask what that means? Sorry, I don't want to interrupt, but what is that like? What exactly is Claude doing? Is it saying like move the robot forward or like change these joint states or move to this position? Okay, you'll get to that. All right.
I have like a couple of slides to explain, and then I will show more examples. So let me just quickly. So there are different ways how you can do it. And so, for example, usually when you create these VLAs, you like add some special tokens that represent actions, and you train it and so on. But the pure LLM doesn't have any extra tokens. So how I decided to integrate it, I decided to do it using what's called MCP. So MCP, Model Context Protocol, is basically standard that was proposed by Anthropic actually less than a year ago. It's pretty new protocol that allows different LLMs and different applications that use LLMs. It allows it to use external tools. So for example, when you use ChatGPT can like search internet, or when you use like Cursor for coding, Cursor can edit your files. It means that like somewhere inside this like client logic, there is some way to implement this tool calling when kind of LLM, instead of just generating text, can do some extra things. And MCP is nothing but like standard that allows all different clients and all different LLMs kind of use the same API to do this tool calling. So you implement it once, and then you can connect it to any LLM application and use it. I will show. So I can actually control my robot from Cursor or Windsurf chat. So like I can control robot from the chat in the code editor. That doesn't make much sense, but it kind of works. So how it actually works? So I implemented what's called MCP server. This is the like piece of code that can actually control the robot. And this MCP server has a few tools. It's simply, you can think few API methods that LLM can call. And in my case, they're pretty simple. It's like get robot state. It's when it returns. So when you send this command, you get back the positions of different motors of robot and the images from the camera. Then it can control gripper. So it can open or close it. Just send the number from like 0 to 100 to represent the like percentage of openness. And finally, it can move robot. And for this moving, we use kind of simple interpretable commands and parameters for LLMs. It literally has parameters like rotate n degrees to the left, or like move 5 centimeters forwards, 5 centimeters backwards and upwards. So I would say out of 6 motors that I have in the robot, like 4 are controlled basically directly. They just control like one dimension, and robot can send the command for this dimension. And only like these 2 motors that control the shoulder and elbow, they're not controlled directly, but I use some very simple inverse kinematics. So it's like very, very simple couple of formulas that instead of kind of changing each motor separately, allows you to say move forward by X centimeters, or move upwards or downward. But the rest doesn't use any inverse kinematics. It's just rotate to the left, to the right, rotate like gripper clockwise, counterclockwise, and so on. So this is what's happening. And it means that inside LLM, it sees something like this text on the left, like blah, 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 you are like a helpful AI assistant. So, and then there is some added text, like you can control the robot using following commands and send like some special token and with parameters, and this command will be executed. So this is on a high level how all these things works. And again, so it's kind of one implementation, then can be integrated with very different clients that use LLM. Some of them have limitations. So for example, I tried to use Claude Desktop for this, and turned out it doesn't have access to cameras. So it was like a little bit complicated. So you need to have sometimes you need to kind of go a little bit more and implement some extra solutions, but generally it worked out of the box with many things. And now let's quickly try to show some demo. So demo number one, very simple. Here on the right, you can see the chat inside Windsurf. It's AI-driven code editor. And I'm using Gemini 2.5 as a model. And this model controls the robot right now. So you can see that on the right now, for example, you can see the results of tool calling. So it requested the object state and received this JSON with position of the gripper, position of the robot, of different motors, and 3 images from 3 cameras. So this is exactly what LLM can see. So it can interpret what's happening on images, and it can keep sending commands like rotate robot right angle minus 30 means rotate 30 degrees to the left. So you just run it in agentic mode. So it means this LLM simply in this infinite while loop, calling different commands and then calling LLM, and then until it decides that it's finished the task. So sometimes it can be pretty slow because the answers from LLM take some time. So it's definitely not the best way to control robot for this simple task. So if you train simplest policy possible, it will be, I don't know, probably it will have higher success rate and higher speed, but it wasn't the goal of this exercise. The goal was to actually test how good this LLM works with this robot control. And you can see that eventually, after some time, the robot managed to grab this ball and lift. Again, with zero training, zero fine-tuning, and so on.
It's so impressive that does that.
I have so many questions.
Sure. You can maybe start asking.
Okay, so some context. I've done something like this, like with our own experiments, but we didn't use the MCP. We literally just used a context window, but we put a lot more things in the system prompt. So for example, I'm curious, like for example, the robot state, right? You have some range. Let's say maybe a certain motor servo can only go from, I don't know, like negative 90 degrees to 90 degrees. Let's say, right?
Yes.
Do you put that like thing in the system prompt, or otherwise how would Gemini know like what does those numbers mean, or is it defined in the MCP client server?
So first of all, I transformed all the numbers into the actual angles and distances. Actually, so at the moment when I first implemented it, it was the default way in the robot. So all angles were already in degrees. So it was more or less easy. But when I just released it, they changed their logic, and now it's also like everything is just from minus 100 to 100, depending on the whole range of motion. So I needed to add like some extra calibration layer. But what I do, first of all, I transform everything into degrees. So maybe if we go I can try to show some of the messages here. Okay. So you can see robot state is robot rotation clockwise degrees minus 30.1. It means that it's rotated by 30 degrees overall from the original position. And then there is this gripper height and the linear position. It's simply linear coordinates of this like axis where the gripper is connected relative to the like point in the bottom of on the base of the robot. So this kind of all these things are more or less interpretable, and it allows actually LLM to understand it better. And I don't put too much into the system prompt itself. So what I did, I add some overall explanation of what it's controlling. That is like some robot with 6 degrees of freedom and so on. And I also added some simple comments on the most, let's say, popular fail reasons. So for example, quite often it's when it's like moving, it ignores the fact that it can hit some other objects, and you need to tell it. So like whenever you move right, left. I don't know, rise the object a little bit up before moving. Otherwise, you will hit other things. So sometimes it's missing some simple things. But to be honest, it's not extremely important, and it's not really following all these commands too well. So if you kind of strip it from all these extra comments, it still works more or less the same. So it's like slightly improves the success rate. So I would say eventually the system prompt is not very heavy. I don't give instructions how to do stuff step by step and so on. I just give some. If I see that it consistently makes the same mistake, I kind of add one line like, don't make this mistake.
In the system prompt? Or do you do it at inference?
In the system prompt. So like if I experiment and it's always makes the same mistake every single time, then yeah, I added the system prompt. It doesn't really solve it all the time, but sometimes it helps.
And then could you share again, what is the at inference? What are you exactly typing to Gemini before you go into the agentic mode? Like I saw briefly. So this is...
let me find it. It should be in the very first. Okay, for some reason, I probably cut video a little bit early. So it's here. Grab the ball and lift it. This is it. This is what I asked. It's on the top right corner. Yeah, that's all. That's all you are prompting. Yes.
And then it said, okay, I can help with that.
The knowledge of the APIs and stuff just comes to the MCP kind of structure. Cool.
Yes. So this is what I put here also. So actually, I don't, when I use this external tool, like here in the Windsurf, I don't even edit the system prompt because system prompt is edited on their side. What I did, I added one more comment. You can see it here. It says get initial instructions, and kind of I put my instructions there. So actually, this LLM can request instructions if it wants, and these instructions is where I put all this information. But system prompts, I didn't even touch in this particular case.
And the instruction is inside your MCP client.
Yes.
Okay,
it's one of the functions that it can return. Yes.
So I suppose is that where Gemini gets the information of like what does negative 100 mean?
Yes,
like,
yes.
Oh,
exactly.
I see.
It says it says what kind of is clockwise, what the counterclockwise, what this thing means, and what is even the size of the robot. So because when it see the pictures, it doesn't know whether it's like 10 centimeters or like 10 meters robot. Like so.
I see.
I describe it in instruction and say, oh, your robot is like this size. It's a simple manipulator and so on.
Interesting. So you put that in the MCP, but not in the system prompt.
Yes.
I see. So by calling the initial instructions, I suppose those information about like what all the numbers actually mean, then and then based on that, is able to do. And how? Well, I mean, obviously calling Gemini, like I mean, there's a cycle. So it looks like, is it every few seconds you send a bunch of photos to it so that then you do the next thing? It's like, what kind of update frequency can you do now?
I send photos only when LLM kind of requested. So what I do currently for every request, either it's get state request or some movement request, I send the position and photos as a response. So whenever it makes any movement, I make this movement. Then I think I wait like half a second or so to have like better pictures, make these photos and send them back to the LLM. If it requests get a robot position, then I don't do any movements and just return the position and the pictures. So just take it whenever it's requested. I don't stream video or I don't send extra.
Yeah, I'm curious, based on your observation, how often does Gemini think that it needs to see again? Or do you think that it should have asked for help for image more often, or it asks at the right point? Is it intelligent enough to know when to ask for more information, I guess?
Actually not. So what I've seen, it's kind of the opposite. So if I do some stuff and then, for example, I add new objects in front of it and ask to do some like new things, then it just says, oh, I don't see this object. Instead of requesting again and updating data, it actually says, I looked at the previous images that I already requested before and there were no objects. Usually it's kind of opposite. You need to actually, if you added something to environment, you need to say, oh, don't forget to look at it again or something like that.
I see. So it's like an open loop system but the agent is not asking for information frequently enough. But if it gets better than that, then it can. I think what is really impressive about this is the potential to do really open loop, like very dynamic things, right? And so that's why I was asking, like, do you think the AI knows when to ask for feedback? Because I thought I just assumed when I saw this, you're probably like just literally pinging Gemini, like, I don't know, like maybe every 3 seconds you just force feed it, but it turns out you're letting the AI to do even more decision making, right?
Yes. I don't force anything. I just let LLM be free and do whatever they want.
Crazy.
But you mentioned Gemini, but I just want to talk a little bit about other models. And actually, it's interesting because let's discuss it now. So I tested like 3 families of models. I tested GPT, Gemini, and Claude. And if you would ask me in advance which one I think will like win, let's say in this comparison, I would expect Gemini to be the best, and then GPT, and then Claude. And the reason why, because Gemini and GPT, they usually advertise their like image processing capabilities much more. They talk about multimodality, and they position themselves as like more general LLMs and so on. Plus Gemini has this Gemini robotics, and I thought, oh, maybe they already like some of this like training leaking to the main Gemini and so on. So I would expect it like this. And Claude is usually positioned themselves as more like reasoning, for coding or for some reasoning for specific things. But turned out it's almost opposite. So Claude is the best in all my experiments. So I think Claude is top model in terms of success rate, then Gemini, and then GPT. So Gemini is slightly worse than Claude, but GPT is much worse. So GPT is really bad. I didn't get any consistent success rate with GPT. I'm not sure why. So maybe they like model structure is a bit different. They like separate a bit models that are focusing on tool calling and models that are focusing on reasoning. So maybe they just don't have a good combination of tools in one model that's supposed to control the robot, because it's not the use case that I think they're thinking about. But so eventually I think I only like now use Gemini and Claude because they're much better than GPT. And mostly I just use Claude 3.7. I also didn't see much difference between 3.7 and 4. I tested both of them, but it seems 3.7 is like as good as 4. So I just use this model for the most of the experiments currently.
And
this is what I expect.
Yeah.
Have you run into like, or have you stretched it to do really so-called long horizon tasks where maybe you stretch into the limit of the context window? Have you gotten to that range yet, or like not yet?
So not really. So what I see, the success rate actually not so high. I would say for simple tasks like grab some object, success rate is around, let's say, 50%. So it's like sometimes it gets it, sometimes it just gets stuck like 1 centimeter from the object and just cannot do this final move and so on. And when you add more steps, it's kind of going down exponentially. So if you need to grab object and then move it to some, I don't know, box, as we'll see in the next video, then you kind of divide success rate by 2 again. When you have like 3, 4, 5 actions needed to complete the task, the success rate is very low. So I tried some stuff, but it's not. It's really hard. You spend like a lot of time to actually get success.
I see.
So reasonably, maybe it can do like 3, 4 actions in a row, but then it's after that it's very low success rate.
So in a way, now you're not bottleneck. You're not even using the full context window. It's more just like after 1, 2 steps, it basically can't carry on anymore. They can't even get to the third steps.
Yes.
Interesting.
Another problem. So I think when I use this. These tools like Claude, Windsurf, and so on, and other agents, what they usually do, they send the whole history with every call. So it means that they send all the old images also with every call. And then the actual context number of tokens that is used growing pretty fast. So it's one of the problems. I actually have solutions. So I also implemented my own agent that sends only the latest images. And for the simple tasks, it's eventually reached maybe like 10 to 20,000 tokens in total for the whole task, and this is the range where it's still operating fine. So I didn't try to go to like million tokens context window. I don't know how good it is at this point, but I guess it will be worse than this, of course. But generally for the simple tasks, I can keep it in the range of 20,000, and it works fine. Let's maybe like look at a couple more examples, and then I think you'll have more questions, and we can again like stop and discuss them.
Yeah.
So this is another example, and here I use Claude, and I use it from the cursor. It's another code editor. And on the left are my couple of socks, and on the right there is this cardboard. So I just asked LLM to grab a pair of socks and put them into the card box, and that's it. This is the whole prompt, and you can see that it can successfully do it. So this is kind of a little bit harder problem to solve because it has two steps. But the more interesting for this particular example is to look at some fails. So here I'm using the same model. The only difference, instead of top view camera, I use side view camera. And you will see now some interesting fail modes. So originally it's doing well. It's moving towards the socks. Let's wait maybe 10 seconds. It will grab the socks successfully. Yeah, let's just wait, and then I will talk about it. So yeah, at this moment I thought, oh, it's almost done. We are almost there. It lifted it correctly, and then it turned to the right. So it was so annoying, and the worst part that it did it many times in the row. So I kept running this experiment. It kept doing the same mistake. I was very confused, and I even was asking, so you can see in the video now, I'm asking the LLM, what are you doing, why are you turning to the right, explain me your actions and so on. It didn't manage to explain and said, oh, sorry, you're right. LLMs usually answer you when you find their mistakes. But yeah, so I was really spent a lot of time trying to debug it. I thought maybe I somewhere missed left and right in the definitions and so on. But then I realized what the problem. So if you look at this picture, then you can see that a robot is on the left and the box is on the right. And if you ask, let's say, LLM, explain where is the box relative to the robot, it will say it on the right from the robot. Yes, just looking at this picture, just simply at this picture. And this is what's happening. So all LLMs, they interpret picture one by one, and they don't have real spatial reasoning when they have a video or pictures from different points of view. So looking from just this picture, that is probably the best overview picture in this case. It sees that the box is on the right, so I need to rotate to the right. And this is what LLM is doing. So I realized that they don't have this spatial reasoning. They don't have this embodied reasoning. They cannot really understand what is the direction from the relative position from the robot point of view. And this is a big issue. And so after this, so actually I did this one first, and then I switched to the top view, and as in the previous video. And with this view, maybe I spent a couple of hours trying to complete this task, has zero success rate, and then switch to the top view. And in top view, all cameras are aligned. So left is left, right is right all the time for all the cameras and for the robot. And it did it from the first try. So I was actually very, very happy when it did it with the top view. And yeah, it's it's extremely important to align cameras. So it's when your cameras, so I found that, yeah, if cameras have very different point of views, then it's very hard to LLMs to interpret them. Also, I found that wide lens cameras work much worse, because probably it wasn't trained on this wide lens distortion images when these models were trained. It's much better to use a bit more narrow field of view, but more linear image, because then all these models are much better in understanding what should be done.
Yeah, I wonder if it's if through maybe more detailed prompting, what if you explicitly tell these LLMs that, hey, just be mindful, the camera position that you're receiving is probably from a third person point of view. So if you want to control, can you imagine back in your first thing about from the robot point of view, imagine, and then give instruction. I wonder if more prompt engineering may get you there. Have you tried a bit more than that? You don't think it's just this model just don't have it?
Yeah. Good question. I did try. So I think right now it's actually part of the prompt. So what I did, first of all, I added description of all the cameras. So I say, okay, you have 3 cameras. This is the position of each camera, to make sure that they understand what they see from each point. And I also explicitly say that pay close attention to the relative positions, don't miss left and right. So I added some text. I think it adds a little bit to the accuracy, but still it's not solving the whole problem. So I think it's still not there. So what I think happening inside LLM, they probably just somehow process each of images one by one. And whenever they really look at this image, the real interpretation will be that the box is on the right, and then they kind of deal with this information. So I think they're still missing this like multiple points of view stuff. Probably it's not a usual training scenario. I don't think they train these models with many images from multiple views.
Did you see any difference between? Did you see any differences between different models in terms of like multi-view, or are they all basically the same?
Not much. I think what I see the difference is instruction following. So I think even so Claude is generally better, it's also ignores my instructions much more often. So Gemini performs a bit worse, but at least it follows instructions. So if I say, for example, that sometimes not a mistake that robot did in this case, sometimes it wasn't lifting socks high enough. And when it rotated to the left, it just hits the box a few times. So when I add to the system prompt, kind of whenever you lift it like at least 20 centimeters from the ground to not hit objects and so on. Gemini is doing it every single time. Claude still quite often ignores this instruction. So I think that Gemini is a bit more instruction following model. Claude is a bit less, but both of them not very good with this multiple points of view reasoning.
It is still mind-blowing though. Like whatever you've done here, you kind of vibe coded what used to take a PhD, maybe an entire PhD to do. Yeah,
but I think like crazy. A lot of it just because we have all these LLMs available. So of course I didn't make the LLMs themselves. They do most of the work here. But yeah, I agree. Like I think the iteration speed is so much faster. Even comparing what I did a few years ago when I did some robotic experiments, I could spend maybe like weeks to do like test some of the tests, and now doable like in one day what before took weeks, and it's very, very cool. Yeah, I want to show like a couple more examples. As I said, if you're talking about this control of actual movements, and yeah, success rate is not sometimes not extremely high, but what LLMs are good at is some kind of reasoning. So they're pre-trained on internet scale data. So this allows them to solve kind of more unclear problems. So in this case, what I did, I put 3 different balls in front of the robot, and one is baseball, another one is for like orange golf ball, and the last one for the squash. And I asked to grab the ball that is used in the racket game. So this is not just like a big like grabbing task for the simple policy. It's actually requires some world understanding from the model. And this is what happening. So you can read some thoughts of the model here, and it can correctly recognize all the balls. And it's like reason that out of these 3 balls, maybe the black one looks like the ball for squash, and squash is the racket game. So this is what I should grab. So this is actually pretty cool because it's hard to imagine if you like train some policy without any pre-training for this policy to understand what is the different types of the balls and what exactly should be grabbed. And in this case, it actually took much more time to grab the ball rather than to understand what to grab. But it's very cool that this model, without again any extra fine tuning, can understand what was asked in this normal language and actually do the job. So yeah, it took some time to grab. It hit this ball a little bit, but then eventually it managed to do it. So yeah, this is kind of another example of what it can do. So I think ideally, if you want some even better policy, we probably need some more like low-level, small policy for like this system 1 kind of that actually moves the robot. But we can directly use LLM without any pre-training for system 2. So for some reasoning and so on, and then this policy this LLM just need to say what should be grabbed, what should be moved, what should be done, and then the actual movement shouldn't be done by LLMs. It's just too slow. It's just too not so precise and so on. But yeah, for this high-level reasoning, they're more than enough. And then I think I have like final video, and after this video we can do a bit of live demo too. And this final video is about this CLI agent. So as I said, using this third-party clients has some limitations. So what I did, I created this CLI tool that can use one of these 3 models and allows you to control the robot using natural language from the terminal. So this is basically the same idea as a chat and cursor as I shown in the previous things, but it's running in the comment line, and it's more optimized. So, for example, I don't resend all images. You can control how much thinking you want to use for each model, so to optimize token usage or speed of the robot. Yeah, this is more or less how it works. So while it's still showing, probably let me prepare a little bit. I need like 1 or 2 minutes, and I can do the live demo, and we can ask robot to do some stuff right now.
Yeah, sounds good.
So I need bit of setup.
Can I ask another question? So I noticed you've got a RealSense mounted on the top there. So why did you do that?
Okay, it's a good question. So I don't really use the depth channel right now from the RealSense. The only reason why I use RealSense because I have RealSense. It just has a good RGB camera, and it's like very easy to mount to the robot. So this is why I mounted it there. So in this particular case, I don't really use the depth thing. I didn't try to send depth channel to LLMs. I don't think they can actually process it well. Yeah, so I just send a simple RGB image from this camera.
Well, yeah, one of the reasons why I was wondering is because you talked about the like them having trouble understanding spatial stuff, and of course, like the depth channel can help. Like you can use it for that, but that involves way more like prompting and architecting and so on. I think probably to get, I would assume.
Yes. I expect that it will require a lot of prompting to actually make it work.
Right. How do you like the Kiwi? I really like those robots. Such a cool little design. Like it's yeah.
Okay. I think I almost
ready.
Okay, let me try to change sharing. Interesting. I cannot change camera right now when we are recording.
We could stop recording and then resume.
Yeah, you can leave and then join again. I mean,
okay. Let me try.
I can always like cut this part out. No worries. Yeah.
Okay. So let me try to rejoin.
Yep. Sure.
Well, or we could stop recording and then resume recording. Right.
It's fine. Yeah. I mean, I guess.
Okay.
Yeah. It's actually easier to be one continuous, and then I'll just cut halfway.
And then you cut it. Okay.
Yeah.
Huh. Nice. Makes sense.
Yeah. Oh man, this is so cool, man.
Yeah, I love how easy it is to do this stuff now. It's like I like the agent for this. A lot of fun stuff. Yeah,
it makes you wonder.
It's so impressive that it just works, right?
Like, it makes you wonder. Like, what is the path to solving embodied AI? Is it just going to be GPT-10? Maybe that is the thing.
I mean, to some extent, like I don't know.
Okay, anyway.
Well, no, GPT was the one that didn't work, right? It was the Claude and Gem. You're right.
That's right. It could be Claude.
Yeah, it'll be Claude.
Yeah, so can you see the full video with robot, terminal?
Yeah, I can see you and you see the robot, but Chris, your camera suddenly become black. Are you still there?
I can see Chris.
Oh, you can see Chris? Okay, then
okay, all right.
Okay, that's fine. For some reason I can see, but it's okay. Yeah. All right, cool.
Okay, yeah. So let's just start and see. Again, this is the Claude 3.7, and this is CLI agent. So let's ask it to move 10 centimeters forward, and let's hope it works. So yeah, we get some requests, we get some results. It requested things. It requested robot state. It's really bad. I don't like it because it's it's not even the error on my side this time. Let's try one more time.
Would it be possible to switch to Gemini?
We'll switch to Gemini. If it doesn't work, we'll switch to Gemini. Okay, so now we use Claude, and let's try to ask it to move, let's say 10 centimeters forward. And the first, it's supposed to Claude is very, very overloaded. They have some issues probably right now, so we're unlucky. Sorry, it's not working. Okay, we'll switch to Gemini now. Sorry, Claude.
It's fascinating. You just do the switch, talk to another brain, and try again. Yeah.
The name is like this. Okay, it seems it works. Okay, now we try to use Gemini 2.5 Pro. Okay, move 10 centimeters forward. What's happening? I'm so sorry that it's not working today. I already tried it. Like I tried it to test it yesterday with Claude. Let maybe try to use Claude without thinking. It takes less resources, so maybe it will just work. Maybe it doesn't like thinking request. Okay, so we're using Claude without thinking. Now move 10 centimeters forward, gets instructions, it's estimate the position, and now
nice.
the robot moves. Yeah, so this is like you can give like very simple commands. So it's like Claude has some problems right now with the API, so sometimes it will return this errors. It's happening on the Claude side, but let's still try to iterate a little bit with it. So let's ask, what do you see? It says it moved 10 centimeters. It describes front camera view, shows some wooden desk surface with some small toy. And yeah, I have this toy here. And then wrist camera, close up of the robot gripper. So it understands what it sees, so it can say what it's happening in front of different cameras. Let's try another simple thing. So let's ask move 10, let's move 5 centimeters in the direction I'm pointing. Oh, and I will try to point like down with my finger. I hope I'm in the camera. I'm not sure if you can see me, but it should see me in the front camera. At me first and then move. So this is what I'm talking about. So it's actually not requesting the information itself. It's tried to look at the previous camera and I didn't show anything. So now it should request robot state. Yes, it requested robot state with 3. Oh no. Try again, like really bad timing. Probably this is when a lot of people using.
Nice.
No, okay, so it's not working very well today. Really sorry for this live stuff. Okay, let me try to stop it.
Maybe it's turning to face the big green. Isn't that what you asked for? I don't know. Okay, yeah.
I don't know, but maybe what we can do, maybe we are a little bit out of time and we didn't even touch the second topic. Should we try to talk about another topic and then come back? Maybe Claude will solve the problems there.
Yeah, you still have the
or do we need to finish now?
Yeah, you still have the last one,
the
dot policy. Maybe you can talk
I'm just not sure, are we limited by 1 hour or we can kind of talk a bit more?
Yeah, we can go over a bit.
We can go over.
Yeah. Okay, so then let's try to talk about it and then we'll come back to this demo. I hope it will work better. I really hope they will fix the API issues by that moment. Yeah, I think I need to reconnect again to change my camera.
Yep, sure.
The downside of relying on an API.
Well, I really wonder. Anything live demo is is Murphy's law.
Oh yeah, anything live demo. That's fair. It's not just relying on the API.
That's why I say he's a brave man. Yeah, but it's also not his fault, right? Clearly, it's but yeah, there's an issue with an intelligence that is not local, right? It's somewhere in the
wonder
cloud.
if like one of these offline, like the Gemma 3N or something, would do it. Probably not though. Pretty dumb. All right.
Yeah, I really hope that it will work when we try it again next time. Yeah, for some reasons, probably time when a lot of people are calling Claude, or I don't know why, and they're busy. So
maybe the secret is out. Everyone is using Claude for the robot,
Yeah, maybe. Yeah. Okay. So we will try it later. One more time. So now let's discuss the dot policy. Let me share my slides again, and after this we will come back to this slide demo. Okay. So the second topic that I wanted to discuss, it's, as I mentioned, it's on the opposite side of the spectrum. So if on the previous one we discussed how we can run experiments with LLMs without any training at all, with like very big models that are running somewhere in data centers, this is kind of opposite. So this one, in this one, I wanted to create a very simple, lightweighted policy that can solve simple behavioral cloning task. I will go through everything on this slide later, like step by step, but generally, just to overview. So I managed to make this policy. It's really very like small and lightweighted, and turned out that it even works better than other state-of-the-art policy like ACT and diffusion on these two simulated problems. One is push T, and another one is the manual insertion using Aloha simulated environment. Let's just go through it quickly. And first of all, just for people who don't know what behavioral cloning is, I think it's one of the most straightforward way to train your robot. So you record a data set where you complete some simple task many times. I think in case of this task, you need around like 50 data points. Each data point each episode looks like the one on this video. So it contains the video streams from all the cameras that you use. it has a history of all the states, and the state in this case is just the position of every motors, all the motors in your robot. So we have the 6 line, it's like 6 motors positions. And finally, you have actions. These are commands that you send with the leader arm. So it's kind of target positions for all these motors. And the behavior cloning problem is basically to, at any point in time, predict future actions using all the information available up to this point, so any historical observations and states. So there are a lot of policies that solve this problem, but when I was learning about it and when I was reading different papers, I've seen that a lot of good ideas came from actually Gen AI. So a lot of good ideas in this area came from either LLMs or diffusion, image generation and so on. And it's great because they actually pushed these boundaries a lot, and we achieved much better results using these Gen AI approaches. But I had a constant feeling that everything feels overcomplicated. It's not real problems, but it's more like my perception at that moment. So I can give you some examples. So example number one, so diffusion models, they work good for modeling high-dimensional distributions. And this is why they're so good at image generation. And this is why they actually managed to be very good in robotics too. And now they're used in many, many policies. But when you think about it and kind of try to compare what is the high-dimensional means in these two different problems in image generation and robotics. So let's say you want to generate one image 1,000 by 1,000 pixels, and each pixel has 3 numbers in it. RGB, then it means that you have actually your output has 3 million dimensions. So all possible 1,000 by 1,000 images, it's 3 million dimensional space. But when you think about robots, let's say you have 30 degrees of freedom, humanoid, and you want to predict 100 times per second, and you predict 1 second chunk in advance, it's just 3,000 dimensions. It's still a lot. It's still very high dimensional, but it's 3 orders smaller dimension that you're trying to predict. So my kind of hypothesis was maybe we can use a bit smaller and more simple models too to deal with this problem. Maybe we don't need such a heavy models for this. Another observation is that Gen AI models allow to sample new predictions from the distribution every time. So for example, I don't know, if you want to generate images of cat, you kind of expect a new cat every time. You don't want the same single image to be generated every time, and this is essential for the image generation. In robotics, there are also use cases when it's important, when you want a little bit of some statisticity, variability of the robot actions. But in most of the cases, you wouldn't trade it for success rate. So success rate is probably the most important thing. And if you achieve success rate by doing the same thing over and over again, maybe it's fine. So again, some things that are very important for Gen AI are not so important for robotics. And I thought, can we try to avoid it too? And finally, one more thing is tokenization. Again, it's very kind of often used thing in robotic policies because it allows you to, first of all, deal with multimodality. When you switch from continuous to discrete actions, it's kind of natural to deal with multimodality. And also it kind of compress information better and so on. So it has some nice things. But again, it's very important for text because text is not continuous by default and you already deal with tokens anyway. But for actions, it slightly feels strange because we have these continuous actions. Then we compress them into some tokens that are discrete, and then we decompress to continuous, and then we probably lose some information on the way. This is why some models have some extra model on top of it. So on top of like VQBet, on top of the token predictions that you decompose, on top of all this stuff, you also have another layer that predicts extra small continuous corrections. So I thought maybe we also can simplify it. And yeah, so I kind of had all these feelings and I decided, okay, let's try to make some very simple policy. My expectation was that I will make the simple policy. It will probably fail, have very low success rate, and I will start adding this complexity and finally understand why we need all these things. So then I made this policy, and the architecture of the policy is on this slide. Maybe at the first glance it can look a bit complicated, but I would argue that it's probably the simplest policy possible when you deal with this type of input data and this type of output data and want to predict some sequence of actions. So just quickly, just step by step, what's happening on this slide. So first of all, I have two types of inputs. One is images from cameras. Another one is states of the robot. It can be like robot state or environment state. And what I'm doing is I simply project them into the same space so we can deal with them later. Simple ResNet backbone to project all the images without any like spatial softmax or without any like extra splitting it into the pieces. Just take one image, ResNet 18, and get like one vector as an output. And I'm doing similar stuff with just simple linear projection for all state vectors. So again, this is the simplest way to move them to the same like latent space for the same like the dimensions. The next thing I do, I just send it as a memory to the transformer, and I use I use simple transformer. It uses only transformer decoder. There is no encoder at all, and it kind of refers to all these vectors using cross attention. Then all the things in the bottom of the slides are simple like positional embeddings and positional encoders. So this is just technically how transformers work. So if you deal with transformer and you have some like time or any other like connection between the tokens, you want to send this information to transformer, and you need to use some type of encoder. So here I use embeddings for the this observation data, and I use simple sinusoidal encodings for the input for transformer that is used to predict actual action. So again, this is just the technical way how you work with transformer all the time. And then basically the main logic happens here. So this transformer simply applied to the this sinusoidal positional encodings predict some vectors for all the actions, all the whole chunk of future actions in the latent space, and then uses linear projection to transform it back to the original action space. So some stuff may seem complicated, but again, generally I use very, very simple things, very straightforward things that you would do with this type of data. You can also, I think my policy is the most similar to the ACT policy. So if you take the ACT policy, remove everything that's related to variational autoencoder, remove completely encoder from it, remove this extra logic, how they deal with images. They like split it in multiple like tiles and transform somehow like separately. Kind of basically take ACT, remove two sort of it, where I think the most of complexity lies in this policy, and you will get my policy. So it's like very, very similar, but just very simplified. So yeah, like I made this policy, and my expectation was that it will perform worse than. But then I ran some tests and realized that it's already this vanilla policy that maybe took, 200 lines of code. It already performs on par with diffusion and ACT and VQBet on some of the simulated problems. So then I decided to add like extra like few steps and extra like improvements for the logic to eventually beat them even like more significantly. And I will quickly go through these extra logical steps that are important for the model. So the first one, optimized a bit the way how I use past observations and how I do like action chunking prediction. So this chart represents our like past and future observations and actions. So this is the x-axis is time. I assume that we are currently at time t. So it means that we know all the observations up to time t, and we know all the actions that we used up to time t-1. So we know all this stuff to the left to this blue dotted line. And what we want to predict, technically we want to predict like next actions, but because we use some action chunking, we want to predict like some number of future actions. So first of all, the first optimization that I did, I actually split inference and training horizon. So when I train the model, I use longer horizon for this prediction. So model can train to predict some longer, more complex actions. But in practice, anyway, when we do action chunking, we do some exponential weighting of the predictions, and the predictions for the very like long future, they have very low weight and they're not so important. So to optimize inference speed, I use much like smaller inference horizon for these predictions that helps model to run faster. And then on the observation and input side, so there are like different approaches. So you can use, for example, only the latest observation if you assume that your process is like Markovian, that like the current position and the current observations explain everything that happens. But in practice, it's probably not the best approach. So quite often in policies, there are like some few historical observations are added because then you can predict, actually, the speed with which the robot is moving right now and so on. But the problem is when you add, let's say, last 100 observations, then you have a lot of extra data that you need to process. It will work slower. And also all these fast observations are extremely correlated. So like the difference that happens in like 10 milliseconds or like 20 milliseconds is so tiny that it's not really so important. So I optimize these things too. So what I do in my policy, I send some recent past observations, usually like just 2 or 3 recent observations as input. And also I sent one more observation from like farther past. So let's say I look like 1 or 2 seconds to the past and sample one observation from that period. That allows model to see bigger picture, but at the same time it need to process only, let's say, like 3 observations at a time, but not 10 or 20 or 30 observations to see this bigger picture. And I think it kind of get most of the information that is needed, but don't need to process too much data, and this is why it can run pretty fast. And then another like big improvement that help at least for push-T problem. So this is how action chunking generally works. So you at any point in time, instead of predicting one next action, you predict few next actions, let's say 5. And in this case, at point t-4, you predicted action for t-4, t-3, -2, -1, and t. And so on and so forth. So for every like step, you predict like 5 steps ahead. And then when you, let's say, make predictions for t, you make these 5 predictions, but then by this moment, you will already have 5 overall predictions for the same timestamp. And you just average them with some weights, usually exponential decaying weights, and you get the final action that is eventually sent to the robot. What I did, I thought that actually, if you already predict a little bit into the future, why don't we send some future action instead? And why don't we force robot to move a bit faster? So let's say we can, at this point, at point t, let's actually average all the predictions for t-1 and send them as an actual final action to the robot. So it means that robot just simply kind of moves faster, moves a bit faster in this case. And it actually helped. So it kind of helps you to balance between precision and speed. So you can maybe trade little bit precision for faster speed in your robot. And in problems where precision is less important than speed, like, for example, push-T problem, I get extra 5% success rate improvements by just this. And also, it's interesting that I think a couple months ago, I read this article or this post from a figure about the helix model, and they're using something very similar. I think they call it sport mode or so. And they also send like a bit of future actions to increase the speed that a robot operates with. They use it slightly different. Instead of this, they kind of use continuous version of this approach. And for example, they can speed up robot not like integer amount of times, but they can speed up robot by like 50%. It means they will simply interpolate between t and t1 action somehow, and then use it as the future prediction. And they said it's really helped them. So they said that this 50% improvements, it's really good. And I think this idea is actually better, because when I try to go even further, when I use like this parameter, set it to 3, 4, 5, it starts failing. So probably the optimal is somewhere between 1 and 2. I used 2 just because I didn't implement this continuous version, but they implement continuous version, and they say that for them, this interpolating between action t and action t+1 gives the best result. So yeah, so I think this idea works even outside my policy. That is very, very nice. And yeah, I think it's almost it. So I have some other important details. I don't really want to go too much into details just for the sake of time. Maybe a couple of things. So first of all, when I make this prediction, I use L1 laws. And I think it's actually very essential. So for example, Act Policy also using these laws, but they kind of talk about it in just one line in the paper, somewhere like just a little bit, or by the way, L1 worked a little bit better. And they even in the pseudocode, they use MSC, they don't talk about it. And then somewhere like in the paper, there's a little bit like a note that L1 works better. But it's actually very essential. So like if your data, if your actions that you try to predict have multiple modes, if you deal with multimodality, then the L works so much better than L2, than the MSC laws, just because it sticks to one of the modes usually, instead of predicting something between them. So when I train my policy, exactly the same one with MSC laws, it completely fails on the problems like push T, but L1 laws makes the success rate very high. So it's like very tiny thing, but in practice very important. And finally, another important thing is that I used LoRa to fine-tune image backbone. So if we go back to this picture, so we have like this very big picture. The thing is, this small block that's called visual backbone, even so I use very small one, it has 12 million trainable parameters. But the rest of the model combined has just 2 million parameters. So like this like small block is actually 85% of all parameters, even so it's not even the core part of the model logic. It's just a thing to transform images. So it's so it's kind of, it leads to a lot of overfitting, because most of your like weights of the model are somewhere where you don't want them to be. So to deal with it, I use LoRa pre-training that reduces the number of trainable parameters to, I think, 0. For this particular part, and it really helps a lot to deal with overtraining of the model. Okay, so these are the main parts of the policy, and then I tested this policy on these two simulated environments that also quite often used in different papers. So one is push T. It's a simple two-dimensional problem where you need to push this T-shaped object to the target. It's pretty simple, but it has multimodality. You can go around this object like clockwise or counterclockwise, and it creates a lot of problems for some simple models. And then the second one is simulated environment of Aloha. And in this problem, you need to control a bimanual robot and insert like one object inside another. The only reason why I've chosen this particular environment is just they were implemented in the robot at this point, and they were just simply integrated and just plug and play. So I didn't need to do anything else. And yeah, this is the only reason. I actually think that maybe for more complex tasks, I'm pretty sure my policy will not work as well as it works for the simple one. But yeah, this is what I trained on and tested on. And you can see the results here. So I managed to improve success rate for push TT points by almost 10%, for images by like around 6%, for Aloha insert around 8%. And all this with using much smaller models, especially like here for key points, like I have 2 million parameters versus 200 million parameters in the diffusion model that was state of the art before it. So yeah, like I managed to make it very small, very efficient, and it even worked better on this simple problems. And finally, let me show how it works on the real robot. So this is example of real robot doing this task. So yeah, going back to the question that we had before, it's running on MacBook right now, MacBook M1 without any GPU. This is real-time speed, and it makes like 25 or so predictions per second at this video, and I think it works pretty well without GPU. And also you can see on the right that it can successfully adapt to the changing environment. So when I see this cup, it understands that it should change the direction and go to the new location of the cat. So yeah, this is it for this part. So this is another example of experiments that you can do with the robot and with with this robot with standard open ARM 100. Yeah, this is easy to do at home. As I shown you, you can run it on your like dining table, and you can even develop your policies, train your policies, and so on. So yeah, this is just some examples of what I'm doing and what anybody can do with this affordable robotic stuff.
Firstly, thank you so much for sharing. I don't know how you do this as a hobby. It feels like you
very
do this
impressive
as
stuff. Very cool. Yeah.
There are so many like neat tricks and tips that I guess maybe not research, but then clearly engineering things that you tested it out in and makes a big difference. Maybe you can say it's simpler task, but you use a 2 million model, a 245 million model, improve by 10%. It's not trivial. Yeah, this is really cool. I would say both part of your presentation, like just cool for very, very different reasons. Yeah, I mean, how the second part especially, do you intend to like write a paper or some kind of blog post about? Have you actually written about this yet?
Yeah, so I didn't write like a paper, but I have very detailed GitHub repo with. I try to stick to more or less paper format, even so it's not formally a paper. But yeah, like I describe everything, and I have all the code, so we can reproduce all these things. So all of this is published in my GitHub repo. So yeah, anybody can try to use it. And I also posted all the trained models on HuggingFace. So all these things are available there. Yeah, I'm not sure. So I don't have any academic background. I never actually like wrote papers. So I'm not sure exactly how to do it and why. And probably this is the reason why it's like stops me. So maybe next time when I do something similar, I should write a paper. I'm thinking about it, but
yeah. Right, yeah, you can just write up a white paper, put it on archive. Why not?
Yeah.
Yeah. Maybe.
Well, or just come onto the podcast and show like we have researchers dialing into this, and but I just find it so fascinating that like literally some of these tiny things that you tweak, like just L1 loss versus L2 loss, right? If you have not spent the amount of hours that you have spent, you may not know this alone can make or break.
Yes.
Sometimes you may make the wrong conclusion. This model doesn't work when actually you just maybe change the loss function.
Yeah,
and
I mean,
so all these things actually matters.
Yeah, I mean, a lot of these are the kinds of things that are like, I feel like you would historically have you get at like an academic conference or something, and I'm really like that we can just talk about them now, and they're so much more. It's part of this whole thing being so much more accessible, and that like it's great to discuss things like that. I guess basically, yeah.
Yeah, but anyway, like I said, I'm so sorry I could hop off. But Ilia, I'm so glad you came on. We asked you to come on. Like, it's super. You explain things very, very clearly. Plenty of demos, and I think you're really brave to try it. And it kind of worked just now. If not for Claude, like you could have worked a lot better. But we should definitely get you in. Back. I don't know, maybe like 3-6 months later. I'm sure you have new experiments to share.
We'll do the demos. They'll work this time.
Yeah,
it'll be.
Thank you. Right. Thank you very much for inviting. Yeah, by the way, we probably can try. Yeah, you need to leave, but we can maybe try to stay with Chris for like 10 minutes.
Yeah, I'll stay on for 10 minutes.
Okay. Let's try.
Okay.
If no,
we'll try one more
perfect.
time. That sounds good. Yeah.
Okay, cool. You guys keep chatting. I'll leave first.
Thank you. Thank you very much.
Yep.
You're welcome.
See you.
Yeah.
Then let me reconnect with another camera and try again. I really hope we will
Hopefully,
make it. I really hope.
Although I'm also not the host, so hopefully hopefully you don't need to be let back. It should be fine. Well, go ahead.
I think the recording is still happening. So
yes, it is. Yeah, you should be fine.
Okay.
Yeah.
Okay, let me leave and reconnect.
Anyway, hey, okay, I see you back. Let's give it a shot. I can see you. Yeah, you don't need to worry about that. Yeah, the uploading thing you just kind of leave in the background. Don't worry about it. Yeah.
Okay, so I hope it will work because it says I have like another tab open and it says it's too many tabs. But I think it works. I just think it will take some time.
I don't know.
Yeah.
I think it's fine.
I just hope we will not lose like any part of the video.
No, it's okay. We can always redo it. It's okay. We've done that before.
Sure.
Things go wrong. We can handle it. It's
Okay, sure. So you should be able to see my screen now.
Yeah, I can see everything.
Okay, so let's try to run this agent.
Fingers crossed.
Yeah, okay, it's running with Claude 3.7. Let's ask it to do a simple task like move 10 centimeters forward. Okay, it's requesting some initial instructions. It's getting text in it. Oh no.
We still have our API error. Okay.
Yeah. Let me Google if they have any problems.
That's surprising, honestly, right? I don't actually usually use Claude, although apparently I'll have to because everyone says it's the best.
Yeah, so this particular error happens when something fails. Yeah, so they have kind of yellow and red. Yeah, so I just opened this. They have this system operation report, and they have some red and orange things there. But okay, let's maybe try a couple more times because it starts thinking. Yeah, so it's actually doing stuff.
It did get
not completely. Yeah, it's not completely off. So maybe we just getting unlucky and get lucky 2 times in a row.
Yeah.
We
can try a couple more times. We can always just schedule, we can always just meet up do another video call for 20 minutes some other time. I don't know how easy that is for Michael to splice in, but it's
let's see.
Let's see. Give it a shot. Let's give it a shot.
Yeah, let's give it a shot. Okay, so I'm running this agent using Claude 3.7, and let's ask robot to do a simple thing. Move 10 centimeters forward.
Okay.
It's working.
There we go.
And so far it works. It got the state. Okay, it moved. It's good. So this time it works. So let's try to maybe ask what it can see. Oh, I don't even need to ask what it can see. It's already saying that, I can see front camera view, top view, wrist camera. Okay, so let's do another thing. So I will ask it to move 5 in the direction I am pointing to. And I'm sitting in front of it. I will try to point down in front of the front camera.
Okay.
So let's see. Hope it can see me. Okay, it didn't. So this is the point that it doesn't actually get new images when not prompted sometimes. If I say look again, it should probably try to request images. So it's again the same problem. Yeah. Okay, so we have, let's just try again. So this is some issue that happening on the Claude side. So the API is not very available right now, but let's try it again. Let's ask move, look at me again, and move 5 centimeters in the direction. Okay, again, I'm pointing down, and I hope, okay, something happened. Now it requested images. No. So something is wrong. So it's tricky. So I didn't really spend time doing some save fails and so on. So it doesn't have retry logic and so on. So probably I just need to do it. Add some retry logic to these things to fix it.
We can try again sometime. It's good. Yeah. What do you think is the coolest thing you've gotten to work with this? What is your favorite bit?
So I really like the fact that these LLMs that are not even related to robotics can control robots. So this is really cool. So the first time when I tried it, I didn't have too much expectations that it will work, but it started to work. So it's really, really cool.
Yeah, it does feel kind of magical that it can, unlike it explaining that it can see you when you're pointing at something or whatever. That's it's very cool. A lot of fun.
Okay, so I think then we will not. Do you want to discuss a little bit more? Then I can switch to another camera again, or.
Sure. Well, we can it's also near midnight here, so I think I'm also pretty tired. But we can.
Okay.
Yeah. Why don't we? Yeah. Let's. I guess. Sure. We can switch to the other camera. To have 1 or 2 more questions, and then that sounds good.
Yeah. Okay. And then about live demo, you can see what got recorded and how, and if you need another 20 minutes, you can schedule. I can try to just add a bit of safety things when I don't know, one of every 5th request to Claude failing. I think it's easily fixable by just retrying. I just didn't implement it.
Yeah, we can always try again sometime. Yeah.
Yeah, so I can make it much more reliable.
We have plenty for the video. It's okay. It's really no big deal. Yeah.
Yeah. Okay, so let me then reconnect with another camera.
Sounds good. Yeah.
Okay.
So, all right. Yeah, great. Well, very cool stuff. So we were talking about the LLMs, how impressive it was. I was gonna ask, I guess. So, have you used the wheeled robot, the Kiwi, yet? For too much? You showed a demo of the Android app, right? Have you done much with learning with that yet?
Actually, not much. So I just assembled this Kiwi maybe 3-4 weeks ago, and I was doing some other stuff. So I currently control it with this MCP and LLMs. But it's not support yet the actual movements. So I don't have a command to actually move mobile base in the MCP. It's not so hard to add. I just didn't have time to do it. So I think it's one of the next things that I want to do. I wanted to move around my house and be controlled by LLM and do some.
See if you can clean up your socks or something like that. Yeah.
Yes.
Pick them all off your floor.
Yeah. So I just want they just want to give it more freedom to go around.
Right.
And it's very convenient. In this case, I control it with Raspberry Pi now, but I don't need any compute on the robot itself. Yes, so all
That's
the
nice,
computation is happening on LLM side, so I can just run it and
I've got a Jetson here. I think I need to get one of those to put it on it, put a Jetson on it, like see if I can. No, that's very cool.
Yes.
But I was going to ask what was next. So like, what's the big next project you want to do?
So actually, like as I again doing it as a hobby, I have usually in my head there are like many different thoughts, and like I just keep accumulating different thoughts for different areas. When I feel that there is enough, I just go for it and try to make something that kind of some deliverable results out of it. So I have different things. I want both like experiment a bit with like hardware, try to improve this robot. I want to experiment with, but I think the closest one, I still want to go a little bit deeper into the policies. And I think again, what I did for now, I did a lot of experiments with the simple behavioral cloning. Now I did experiments with the zero-shot LLMs. But I think the best policies are like exactly in between. So all this like VLA policies that basically combine pre-trained LLMs with some extra training on top of like robotics data, showing the best results currently in many problems and many research. So I want to go deeper into it because I kind of read a bunch of papers and so on, but I didn't do much like hands-on with VLA policies. So I probably will be one of the like next things. I want to try what already exists in open source. I want to try to make maybe my own VLA,
like a small VLA,
and so on.
Yeah.
Small.
Have you thought about like using, like, you've got your trained policies? Have you thought about anything like using the having your agent call those, like as part of a
yes.
Okay.
It's not the idea. So I also thought maybe to make this LLM controlled robot more precise, we need some very small policy or maybe bunch of policies that, for example, I don't know, can grab an object that is pointed by LLM. So LLM sends some, coordinates on the image and then it kind of grabs it. This would be interesting, and I probably can try it and actually seen other people doing something similar. They created like very simple policies and they kind of use it as inverse kinematics, so just you say the point on the image and it kind of grabs whatever at that point. So I thought about this one. So I think this LLM should be able to call simple policies from it. But again, it's not implemented yet. But it was one of the in this list of thoughts that I can implement. I definitely had it.
Yeah, sounds cool. All right, one last question that we always ask everybody is like, what have you seen anything else cool lately, or anything like other like on Twitter, any cool research or projects or open source, anything?
Yeah, I would say I don't have like some particular maybe paper to recommend, but what I really like and enjoy and I follow is everything that physical intelligence is doing. So I think they post one paper a month, more or less, and I really like the results. I like the way how they explain all the ideas. So I think it's all their papers are usually very, very high quality, both in terms of results and explanation of the ideas that you can reuse and other things. So I really enjoy it. So sometimes they have very big releases like this Pi or 5. Sometimes they have like smaller about this asynchronous inference, I think they had recently and so on. But I really enjoy like following them, and whenever they post, it's usually very, very nice ideas and cool things. And the demo also very nice. So this is maybe if you're not following yet, so I recommend people who listen in it too. You probably know, but if someone listening and don't know about these things, definitely follow the cool things.
Well, thanks for coming on. It's really cool stuff.
Thank you. Thank you very much. It was very, very nice to talk to you and discuss all these things.
Yes. All right.
Yes. Bye.